Welcome everyone to another video. In today's video, we'll be doing exercise 1S from the IB textbook. So let's go ahead and get started. Question 1 asks that to prove that for n, which is an element, oh, that's a horrible notation, which is an element of integers, if n squared is odd, then so is n. For this proof, we're going to use proof by contradiction. So we're going to assume the opposite of this. It's the first step. Assume that n squared is odd, but n is even. Okay, let me make that readable. We're going to assume that. So this means that if n is even, then n has to equal 2, and we'll just say k such that k is an element of some integer. And that means that n squared is going to be equal to 2k squared, which is equal to 4k squared, which is even. Check that out. And because that actually ends up becoming even, that's the contradiction right here. We said the assumption was that n squared is odd. So the assumption was saying that if n squared is odd, then n is going to be odd. But in our assumption, we said that if n squared is odd, then n is even. And clearly shown here, if we square an n, which is even, then we get up an even number, not an odd number. That is Q, E, D. Number 2. Prove that the square root of 3 is irrational. All right, these are rational proofs, so it's a bit tricky, but we should be fine. For this one, we're going to use proof by contradiction once again. I believe that's what they actually want to use for most of these. So we're going to assume not, as Mr. Shiner would say. We're going to say that the square root of 3 is rational, and if it is rational, that means it could be divided by a and b, such that b does not equal 0, and they're not the same number, whatnot. So now we want to get 3 by itself, so we're going to square both sides, and we're going to get 3 squared is equal to a squared divided by b squared. Oh, whoa, 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 whoa. Just 3, sorry. This means that a squared is divisible by 3, because we can create an equation that looks like this. And that also means b squared is divisible by 3, since we can just straight up divide it like that. Let me get that out of there. That means that we can write 3b squared equal to some number that's divisible by 3 also. Since we know a squared is divisible by 3, it can equal this number, which is equal to 9k squared. So that means b squared is equal to 3k squared. However, this ends up actually contradicting what we said earlier, because we know the definition of an irrational number is that a and b have to have the greatest common denominator, which is equal to 1. But if this is true, that says otherwise. Hence, the square root of 3 is irrational. Hopefully that wasn't too confusing. I'll try to clarify some information on 3 since it's just going to be the same question. All right. Again, it's saying to prove that the fifth root, if I can get that in there, of 2 is irrational. Seeing what we're doing, we're going to assume not. So assume fifth root of 2 is equal to some a divided by b such that greatest common denominator is equal to 1 here. So we're going to fifth root both sides to get 2 is equal to a to the fifth over b to the fifth. This means that a to the fifth is equal to 2b to the fifth. So that means that a to the fifth is even. So we can write a as an even number, which will be 2k here, which is, oh, that's to the fifth, sorry, which is equal to 32k to the fifth, which according to what we said earlier is equal to 2b to the fifth. And after dividing, you get 16k to the fifth is equal to b to the fifth. However, this ends up contradicting what we said earlier. As we said, the greatest common denominator has to be 1. But here, if we're able to divide them by 2, well, if we're able to divide both sides by 2, and that shows that the greatest common denominator is not in fact 1. They're both even. It contradicts what we said. Therefore, the fifth root of 2 is irrational. Basically, what we're just trying to prove for most of these irrational stuff is that their greatest common denominator is not 1. The proof of a rational number is that these two numbers can't have a greatest their greatest common denominator has to be equal to 1. So if we're able to not prove that, then that shows that it is irrational. Right. Going on to number 4, we have that for all p and q, which is the element of an integer, p squared minus 8q minus 11 does not equal 0. Okay, I think all these are actually just going to be contradictions. So for this one, let's assume that that is not true, and that p squared minus 8q minus 11 does equal 0. So then we can separate them on each side, and we get p squared is equal to 8q plus 11 let's actually not separate them. Hold up, give me a second. I have to think of how I can actually end up doing this. Okay, got it. We're going to bring this equation down here. And let's just set p equal to an odd number. The reason why we're going to set it equal to an odd number is because 8q plus 11 is an odd number. That means that p squared is going to be equal to 2k plus 1 squared, which is equal to 8q plus 11. Factoring all that out, we get 4k squared plus 4k plus 1 is equal to 8q plus 11. From here, we're going to combine like terms, minus 1 from both sides, and then factor out, and then minus 8 on both sides. So we'll get 4k squared, 4k minus 8q is equal to 10. And then we're going to factor out the 4 from both sides. And after dividing by 2, simplify it even further. And this is our proof right here. Sometimes you just gotta know when to stop with the proofs. We know that this is a number divisible by 2. So it doesn't, and we know that k and q are just integers. So whatever this is inside of here has to also end up being an integer. So this side is even while this side is odd, and that's our proof right there. Q, E, D. That's a contradiction. So that proves that this is not true, and that it has to not equal 0. Okay, number 5. I'm bumping into my other equations. For all a and b, which is an element of an integer that is bracket 0, for all non-zero integers. Okay, for all non-zero integers, I forgot what that meant for a second. I had to think about it. 12a squared minus 6b squared does not equal 0. Okay, I see why it's saying for all non-zero integers now, because if you plug 0 in there, then it is going to equal 0. So let's assume not once more. Assume that this statement is in fact true. In that case, we can say that 12a squared is going to be equal to 6b squared. Dividing both sides by 6, we get that 2a squared is equal to b squared. This means that 2 is equal to a squared divided by b squared. This means that the square root of 2 is going to be equal to a over b. And whoa, remember what we said earlier. Any rational number can be written as a divided by b. But square root of 2 is irrational, and what we already proved. So this is our proof right here. And that contradicts. Just simple or basic math. That's the answer. Okay, 6. If a, b, and c are elements of an integer where c is an odd number and a squared plus b squared is equal to c squared, then either a or b is an even number. Okay. For this one, we're going to use contradiction once again. Let's scroll down. We're going to assume that what they said earlier was true, and that c is still an odd number here. But b or a is going to be equal to, or b or either a or b has to be an even number. I'm going to assume that. And we're also going to assume, oh, sorry. It said, okay, we're trying not to assume that. Okay, we're going to assume that, and this assume not the contradiction, we're going to assume b or a has to be an odd number. All right, we'll first start with assuming that both of them are odd. If that's true, then that means that a can be equal to 2k plus 1, while b is equal to 2s plus 1. Squaring both sides. We get 4k squared plus 4k plus 1 plus 4s squared plus 4s plus 1. We can factor a 2 from, oh great, I have to scroll. We can factor a 2 from all this after we combine the ones, so then we get this. That's supposed to be a 2 right there. That's supposed to be a 2. However, remember what we were saying earlier, that C is an odd number, which means that C squared is also going to be an odd number. However, if we're able to factor a 2 on this side, then that means this is an even number, and that is our contradiction right there. So we can write QED for that, but there's still more that needs to be done. We only assume they were both odd. The original one was saying that one of them has to be odd and one of them has to be even. So if we prove that both of them odd is not true, then we have to prove that both of them even is not true. So let a squared plus b squared be equal to 2k squared plus 2p squared, which is equal to 4k squared plus 4p squared. And after factoring a 2 from each one of these, oh, did you look at that? Once again, we got an even number, even though we know that c squared is going to be equal to an odd number. And that is another contradiction, and that is our final QED. Since we just proved that when they're both even numbers, it doesn't work, and when they're both odd numbers, it doesn't work, we can assume that one of them has to be even and one of them has to be odd. Okay, next one, number 7. If n and k are elements of the integers, then n squared plus 2 does not equal 4k. Jeez, okay, yeah, these are all contradictions. I didn't realize that. Okay, assume n squared plus 2 does in fact equal 4k. This means that n squared is going to be equal to 4k minus 2, and n squared is going to be equal to 2 times 2k minus 1, which means that this is an even number. So that means n also has to be equal to an even number for this to be true. So then we can plug this back in here and get 2m squared plus 2 is equal to 4k. So then we get 4m squared plus 2 is equal to 4k. And dividing everything by 4, we get m squared plus 1/2 is equal to k, which means that m squared, I should have these arrows on here, m squared minus k is equal to negative 1/2. And this is where our issue arrives. As we said earlier, n and k are elements of integers. So that means that this has to be an integer and this has to be an integer. So when we subtract these two, they should also equal an integer. But negative 1/2 is not an integer. And that is our proof that this is not true. QED. Number 8 asks to us, okay, number 8 says that if p is an irrational number, so p does not equal a divided by b, and q is a rational number, then p plus q is also irrational. Okay. We're going to once again use contradiction for this. So now we're going to assume that p plus q is in fact rational. And if we know that q is rational, we can set this as p plus a divided by b is equal to, we'll do C divided by D since I already used A divided by B over here. So I don't want to make it look funky. This means that P is going to be equal to C divided by B minus A divided by B. Remember, A divided by B is just Q in this situation. Now we're going to do some cross multiplying. P is going to be equal to CB minus AD over BD. Now this is where our problem arises once again. By assumption from earlier, we didn't switch up that P is irrational. However, this shows that it's able to get that it is divisible, which means that it's rational. So this is just not true. That is QED. Okay, time for number 9. Given that m and n are elements of positive integers, with m, I hate when it does that, with m being bigger than n, it is true that m squared minus n squared cannot equal 1. Okay, once again, we're going to do a contradiction. We're going to assume m squared minus n squared is in fact equal to 1. And if you remember our power stuff over here, or factorization, this is equal to that, which is going to be equal to 1. Since m and n are elements of integers, that means m plus n and m minus n are also elements of positive integers. The product of two positive integers can only give 1 if both are either 1 or negative 1. Let's remember that. So these can only give you 1 if they're both equal to 1 or if they're both equal to negative 1. So if that's true, that means m plus n has to equal m minus n. And if once you cancel out m and m from both sides, you get n is equal to negative n, which is just not true unless it's 0. And 0 is not a positive integer, so that is our proof. Alright, getting better at explaining these. Well, I'm getting better at explaining these, I'm hoping. That's true. Alright, 10 is a longer one, but it's also the last problem. 10 says to show by a counterexample that the following statements are not true in general. Okay, it should be easy, I guess. Let's write this down. M plus n squared does not equal m squared plus n squared. We can do it the long way, or we can just set them both equal to 1 and then that gives us the proof already, but we'll do it the longer way. Factoring this out, we get m squared plus 2mn plus n squared is equal to m squared plus m squared. If we assume this to be true, cancel out each from both sides, we get 2mn is equal to 0. And oh, okay. I was about to say, okay, I was about to say, wait, this is true for 0, but then I realized it's asking for in general, and we can already prove this since if we plug in literally any number in here that's just not equal to 0, then this is just not true. So that's the QED for that. Now it's 10a, 10b, the positive integer. So we'll do just positive integer is divisible by a prime number. Okay, well, this is how we're getting funky now. We'll just set p as a prime number. then the number is not a prime. Okay, this is talking about in general, so we can just take any prime number to make this more simpler. So let's take 3. No, yeah, let's take 3. That'll be our first prime number. And it's trying to say that if this number is divisible by any prime number, so we'll do our random number as 12, then the number is not prime. Okay, I should probably take a prime number for this. We'll just take 3 once again, because it said any prime number. 3 divided by the prime of itself is equal to 1. It is divisible by itself, so this is just not true. You can do this with any other prime number. You got to remember that it's talking like literally any number here, so the number could just be equal to the prime itself. Okay, 10c, 2 to the n minus 1 is a prime number for all n. Okay, once again, we can just plug in any prime number, or just any number in here and see which one doesn't work. Let's just plug in, for this case, I think the closest one would be 4, so 2 to the 4 minus 1, that equals 15. And that's just not true since, well, I mean, that equals 3 times 5, and prime number is a number that's only divisible by itself in 1, and this proves otherwise. So QED. Okay. 10D. The sum of 3 consecutive positive integers is always divisible by 4. Okay, so we'll have 1, then, actually, I should write it like this. A plus 1, A plus 2 is always divisible by 4. Let's just go ahead and choose a random number. Let's just say 1. 1 plus 2 plus 3 is divisible by 4 according to this, but 6 is not divisible by 4. Or I should do it like that. So that's just not true. QED. 10E, the sum of 3. Oh, wait, was that 10E? Did I skip something? I did skip something. Oh, shoot. Okay, 10C was asking for all natural numbers, which some people just say it's 1, 2, plus. We just proved that here. But then 10D is asking for any positive integer. And I mean, we literally just proved it with a positive integer over here, so there's no need to prove that again. This is 10E, and this is 10F. The sum of 4 consecutive positive integers is always divisible by 4. Okay, so this one is going to be 4 consecutive positive integers. Let's just take 1 again. 1 plus 2 plus 3 plus 4 is equal to 10. And 10 is not divisible by 4, so that's our proof. Okay, hope you all like this video. This one was a bit shorter, thank God. Proofs do get tricky. Okay, Duolingo, I don't care. Alright, I hope to see y'all next time. Have a good day.